Okay, so picture of a general linear transformation. This is your null space. This is your zero vector over here, obviously. Okay? And you've got the whole thing going on to some range space, right? So we'll call this space R, and that's where everything in here goes, somewhere in the range space. And R might not be a good thing because you could confuse it with rank. Okay? So we'll just say this is a space A of V. Space of all the vectors in V transformed. And that's where they live. And you got, yeah, maybe this space is all of W. Okay? Maybe not. Turns out that this part of the space is orthogonal to this part of the space. Okay? That's just a preview. You don't have to understand even what that means right now, except in terms of what I just said about the importance of orthogonality, especially for engineering. In your case, especially for engineering. I mean, it's important in mathematics, pure mathematics, physics, all over the place. Okay, anyhow. So any row of A, assuming this is, we've got the matrix representation according to some set of bases, okay? Any row of A transposed to a column there's a simpler way to state this, so but I'm going to say constitutes a vector. And let me add one thing because it's important to say this has to be non-zero, non-O0. We'll do it this way: non-zero row of A. Okay, row of A that's not all zeros. Say constitutes a vector in V minus n. So here's n, the rest of it is V minus n. Okay? N is orthogonal, any vector in n, but that comes later. Okay? This constitutes a vector in V minus n. Okay? So what do I mean by that, and why is it true? Well, I'll just illustrate why it's true without being formal, just by picture. Here you have your A matrix, right? And here you have some row, AI1 through AIN, right? So what's the column vector? We're transposing the row to make a column, right? Well, so here we have a non-zero row. Okay? And here it is transposed. Okay? Is it possible that this is the zero vector?